should have taken the picture Monday, there are more people. Okay, so we're looking at the acoustic wave equation. This is Gelfand's problem for hyperbolic equations. This is like propagation of sound, use the pressure. So we're taking a plane wave in the far past. So the sound speed is 1 outside the ball. So there is a plane wave coming in. We want to see how the solution looks like. We are going to look at the main singularities, and we agree that this is going to be an amplitude times distorted plane wave. Call it distorted because t is not equal to x dot omega here. It's going to be something different. This is t equal to x dot omega. This is t equal to phi of x omega. Before we had a plane. The singularities were always in the plane for the case of the potential. Then the Heaviside function as before, and then smoother terms. But so the main singularity is this one. Because this is the delta function is 0 here and 0 here. Right? Okay, so if you plug it in and you try to eliminate the singularities like we did before, then you get this term. This was checked yesterday, I believe, with the second derivative of the delta. And then you want to eliminate this. This is the highest order singularity, and you get the Conal equation. It's a non-linear equation because it's this square, modulo square, and however, it's first order. Is equal to x dot omega in the past, outside the support. This is the support of the sound speed. So sound speed is 1 outside the ball. Any questions? This is we want to eliminate the main singularity, and then this is, and we had also the transport equation. I will talk about this later again. We're going to concentrate now on the Conal equation. I mean the amplitude of this wave. Okay, so this is the transport equation, something that also Rui was talking about for the case when you have a straight lines. As here will be a little bit different because this is not x dot omega. The gradient is not omega here. Okay. So the Conal equation, there is a zero. Yes, sorry. Sorry? Yes, in the ball of radius r. No, 1. 1. C is always positive. Right. Because the sound speed has to be positive everywhere. Right. Of course, you can also require the C decays at infinity, but I'm taking the simplest situation. Okay, so one goes to phase space. This is the Hamilton-Jacobi theory and defines this Hamiltonian. So the idea is that when this is 0, modulo c squared is 1 over c squared, and you want c to be the gradient of some function, phi, to be, this will be a solution of the Conal equation. Okay, so that's the idea of the Hamilton-Jacobi theory. So you go to phase space, to 2 n dimensions. So this is what's called the Hamiltonian, and there is a Hamiltonian vector field, which is the derivative of this with respect to the c variable in the x. These are the integral curves of the Hamiltonian vector field. This is the derivative with respect to c, and minus the derivative with respect to x, the gradient. So you take the integral curves of that vector field. So you have a vector field in phase space. Of course, I cannot draw it because it's at least in 2 dimensions. There will be at least 4 dimensions. And this is the case, it's called the sphere associated to the C, when HC is equal to 0. These are the points where modulo C squared is equal to 1 over C squared. So you start with a point like that. It's in HC is equal to 0, and the geodesics are the projections of these null by characteristics, were called because they are in HC is equal to 0. And Sebastian proved that these curves stay on HC is equal to 0, they start there. And so the projections in the x variable is another way to define geodesics. Also, geodesics are defined by minimizing lengths locally. That's another definition. So this is ds over c. It's the square root of the metric is ds squared is 1 over c squared times, for the people who know, this is the length, the way to measure lengths. This is the standard way, it's called the Euclidean one, and you have a factor here. Okay? And again, because the geodesics try to minimize lengths, they try to avoid regions of low velocity because the lengths will be much bigger as you go through this region. Remember, you have to divide by this. So that's one of that's the case where the geodesics are going to come together and form caustics. We saw in the pictures yesterday. These pictures. Was in this, was not in this. I thought I had shown this picture. Okay, but I know here there. So this, when geodesics come together here, is when they go through regions of low velocity. They come together like this. Okay, so this is where we were yesterday, and then the way to solve this is that you start with this plane in the past, x dot omega is equal to minus r, and you take what's geodesic flow, meaning you take the bicharacteristics, these bicharacteristic curves, and you flow out by this bicharacteristic curve. This is in phase space. Okay, and these forms, so they have an x component and the c component, and this is one of the exercises that we may do in the discussion. This is a Lagrangian manifold here. What is a Lagrangian manifold? And a Lagrangian manifold is locally given by this, as shown by Heim. Right? And so that's the way to solve the conal equation very geometrically. A Lagrangian manifold is an n-dimensional manifold. We are in 2 n dimensions, so that this form vanishes on omega. So this is it's called a symplectic form. So that means when you have omega acting on vectors tx, tc. So a 2-form act in pairs, and let's call it t tilde. This is the x component, and this is the c component. This is the x component, the c component. Then this means it's tx times t tilde c minus tc t tilde x. This is t tilde x. So this times this minus this times this. Okay. You can check that that's the way to check that first of all, you need to check that it's n-dimensional, the flow out. This is n-1 dimensional, this plane. It's n-1 dimensional, so you're going to, because you're flowing out, you are going to get an n-dimensional, and you have to check this is Lagrangian, second exercise. Okay, that's a very geometric way to solve the conal equation locally. Okay, So that's, I think that's where we were finished yesterday. Any questions? Just a review of what we did yesterday.
If you have low order term like convection term or the potential term,
Sorry?
if you have low order term
Yeah.
in the PD, then I believe Hamiltonian doesn't change, iconic
Doesn't change.
but transport equation.
Transport equation, the first term won't change, but the next term will include the potential.
Okay.
Yeah, so
you need the next singularity.
right, right. So you want to recover both. So John Rock is asking the question, suppose you, instead of having the acoustic equation, you have this plus a potential or plus first order terms. For instance, these are usually attenuation terms. You try exactly the same. This is not going to change. What is going to change is this, the transport equation for the A1. The Conal equation was already been chosen. The phi is already chosen. So just changes the transport equation for A1, which I didn't write because I'm just taking the acoustic equation here. So this reflects the highest order terms. So this is a very flexible method. This can be applied to many equations. It's geometrical, it's called geometrical optics. This is. But again, I repeat, the main point of this lecture is to show that special solutions of the equations give you information. So in the part of Calderon's problem, those were complex geometrical optic solutions, behave like exponentials, or in 2 dimensions, a particular were things like e to the phi plus I psi, and there were things like that also in higher dimension. But
you have similar expansion using point source.
Yeah, there is point source that you can take spherical waves instead of plane waves. Plane waves is perhaps the easiest one to take. You can also take spherical waves, like we did for the elliptic problem. What is this? Okay, so these were things like this, remember? And then there was in 3 dimensions or higher, in 2 dimensions too, these are, and the point x0 is outside the domain, the closure of the convex hull. So you take complex spherical waves to probe the obstacle. You can do the same for the wave equation, but they are real. In this case, you have this complex part. So that's the difference between elliptic equations and hyperbolic equations. Questions? Okay. Okay, so here we have this situation, and outside the support of the C, by meaning support of the C, I mean it's 1 outside. It's just a plane, right? Because C is 1, the solution is x dot omega. And then these are perpendicular, you start perpendicular outside the support, and then here the gradient is perpendicular to these curves, which are geodesics, right? Are the geodesics of this metric. My handwriting is getting worse as I get older. And so these measures, because you're going in the fastest way possible, right? You're going along the gradient of the phase function, and these are minimized lengths locally. Then I'm going to assume for these purposes that there is a global solution of the Conal equation. Okay? For instance, if C is close to 1, there is a global solution. And these are we're going to consider more general things later, but those are called simple. Simple, for instance, in this case, where the behavior of the geodesics is very nice. Right? Two points, there is unique geodesic, there is this situation does not happen, but we want to consider this later. Okay, so this is defines the, so this is the geodesic distance between this plane and this plane, because you're trying to go in the minimum amount of time possible along the gradient, as the gradient is perpendicular to the level sets of the phase function. There is there is this phi x, this is distorted plane wave, and the gradient is perpendicular to the level set, right, phi equal to t. So this is called the geodesic distance. So this distance here measured like this. I will define it very precisely in a moment. Here I'm assuming that the conal equation, this is EE, can be solved globally for the moment. Okay, this is, so there is a problem here. From the Gelfand problem, we have arrived at the following information. Suppose you know the phi for x equal to r. So we know the phase function outside. Can we recover the sound speed? So we know the information outside here. Can we recover the sound speed inside? So we are reduced to a problem of knowing these solutions of the conal equation, and this is called the geodesic distance. Can we recover the sound speed? So it's a very simple nonlinear PDE. So we know the solution of this PDE outside the support, let's say outside the support of phi, of C, sorry. Can we recover, from this information, can we recover C? That's the inverse problem we have reduced it to. So we have before the wave equation, which is a lot of information. This the original problem, the Gelfand problem. The Gelfand problem can be reduced to this. If you know this phase function, it's a solution of this PDE. Outside, can you recover the sound speed inside? Right? That's the inverse problem. Question? Okay, so that's called boundary rigidity because I'm going to now I'm going to define the distance function more precisely. So suppose you take a bounded domain. This, for the people who know manifolds, you can consider a manifold as well with this metric that we had before, Riemannian metric, which is given by this. But you can think of, you have a sound speed and you have a domain. You don't need to. Okay, and then you have a smooth enough boundary. And you have 2 points in the boundary, and the distance function, this is the precise definition of 2 points in the boundary, is the infimum of the lengths of all the sufficiently regular curves that join x and y. So you take curves joining the 2 points. So it's a variational problem. You take different curves. So let me draw the picture. Where was the line? I saw the line in a moment. It would be good if they will tell me where the line is. Here is okay. Okay. So you have this situation. You have 2 points, x and y, in the boundary. This is omega. Let's call it omega. I call it m there for the people who know manifold. But think on a bounded domain, and you take all the curves that join the point x and y. Right? There are many such curves that are joining the 2 points. The distance function with respect to c is the infimum of the length of all the curves that join the 2 points. So what is the length of a curve? The length of a curve is the superposition of the lengths of the tangent vectors. But this is, the curve is called sigma. It's modulo d sig dt 1 over c. The square root, as I pointed out before, the square root of ds squared over c, of c squared, so it's this. This is, length is time over velocity. Okay. So this is the length, and then the inverse problem is knowing this distance function between 2 points in the boundary. Can you recover C? Right? That's it's called boundary rigidity in differential geometry, but it's a problem in geophysics. This arose in geophysics. This is the travel time. How much time does it take for waves to go from point X and Y? The first arrival time of waves, because you're taking on the infimum of the length of the curve. The length of the curve is the time. So can you recover the sound speed knowing the distance function? So Gelfand problem can be reduced to the boundary rigidity problem. This is the point of view of geometrical optics. Okay, so instead of this complicated boundary control method that assumes this unique continuation, this is much more flexible tool. So that's the boundary rigidity problem. Unfortunately, we cannot. If this is related to regions of low velocity. If the velocity is very low, remember the metric is this one, 1 over the velocity squared. So if the velocity is very low, the length is very high. So you are not going to go through the point x0, which if the sound speed is very low, because the length will be too high. I mean, remember, you're dividing by c. Here, c, that will be too high. So you're going to avoid completely the point x0, and you're not going to see anything about the point x0, right? Because the curves that minimize the lengths are not going to go through the point x0. There are some curves, of course, that go through the point x0, but this one has to work harder, go through this mountain, and will arrive later at the boundary, right? So you cannot recover in general. So you need some a priori condition to recover C from the sound speed. And here it comes I mentioned this word before. A domain with a sound speed is called simple. Simple is an abused language in mathematics and also in very simple. This is very simple. Well, this is the point here. These metrics are very simple, a very nice behavior. If given 2 points in the boundary, there is a unique geodesic that minimizes length joining X and Y. So the situation in the sphere, for instance, cannot happen. You cannot have too many geodesics going through remember, this is the South Pole. I have been trying for many years to change the map of the world, but without any exit, any success. There is a unique geodesic. So this is, I repeat, this is a very nice picture by Francois, this picture by Francois Bonnard. This is simple. This is the case where it's simple. When for these metrics that depend only on the radius, The radial functions, these are the sound speed, this looks like Gaussian, and there is a parameter k here. For this parameter, the behavior of the geodesic is very nice. Here again, they come together at the boundary, and here they come together in the interior. So only the picture on the left is simple. These are called caustics or conjugate points of the metric. So, and the boundary is strictly convex. Strictly convex means you have 2 points for instance, although this is flat here, you wouldn't think it's strictly convex. It's strictly convex for this metric. I mean, the geodesics, which are drawn here, they have to curve to join the 2 points in the boundary, right? Because they're not straight lines, right? Because the metric is different. And Muhometo had a very nice result that should be popularized more. One can determine C uniquely and stably. That means he proved stability estimates for the simple case. For this, of course, the simple case doesn't cover every situation. For the simple case, he proved that you can recover the sounds with a completely new method. So this was really a breakthrough. And many people don't know about Muhometo. This was in the year is not here, it was in the, I think it's in the 1977 or something. The story that a colleague of him told me, Vladimir Sharafuddinov, he's Russian, that he had not published anything for a long time, and the director of his laboratory menaced him with firing him if he didn't publish a paper. And then 6 months later, he came with this magnificent result. So maybe that's a good idea for when you are under pressure. Sometimes it works. Sometimes it's the opposite. The only problem with Muhometo, his papers are extremely difficult to read, and his lectures are terrible. But he proved something fantastic. Okay, but I want to get rid of the condition that this is the condition of simplicity. Since I'm running out of time, let me I'm not going to talk about these Lagrangian distributions yet, so I'm going to talk about the transport equation. So the transport equation for this case was given in this way. It's a first order PDE, linear PDE. These are very easy to solve. It's called a vector field equation. You have a vector field, let's call it V. This is in phase space, but let me just say this is any dimension. M is called the variable. You have some variable, AI, dxi. Okay, not any vector field. This is a vector field, right? They are derivatives, first order derivatives, AI are real value. And you want to solve VU equal to F. How do you solve this? Or VU equal to, let me do V, you can also solve VU equal to 0. Let's do this one with some initial condition. U, let's say, at xm equal to 0 equal to some function f. Right? Let's assume, without loss of generality, that am is non-zero for all x. So how do you solve this first order? This is the situation here. We have some coefficient here, gradient x, And then we have lower order. We can have lower order terms if you want. We can put some Q here. The Q doesn't matter. And Q is real value as well. Okay, so how do you solve this? This is the situation here. You do what's called characteristics. Let me write it on the right-hand side. So these are, again, characteristics is another name in mathematics that's used a lot for many things. We have back characteristics, remember, from the Hamilton-Jacobi theory, but those were in x and c. These are just in the x variable. This is dxi ds equal to ai of x of s. Right? So this is, you have a vector field, you have the initial surface, you have a vector field that is, because am is non-zero, is transversal, not necessarily perpendicular to xm equal to 0. You have the integral curves here of this vector field, and you just solve, you solve the ODE. So the solution will be DDS, the solution you're looking for, U of xs plus Q of xs will be equal to 0, and x at 0 is f, or let's call it x0. The initial point is f of x0. Let's take x0 to be this point. Right? It's an ODE. Transform into just differentiation. This is very simple ODE to solve. So that means this is the xds gradient of Px. This is what we need to solve, because this is the coefficient ai in this particular case. This is the potential q times. This is something that we know. And so remember, the curves x of s are the geodesics. The projections of the bicharacteristics down are geodesics. So we solve this ODE by simply integrating along geodesics. So we have to integrate along geodesics. So this is the solution. So this leads to the geodesic transform. A geodesic transform means you integrate a function along geodesics that start at the point x and c. So you have.
Could go down a wall. Maybe.
So again, we go to phase space. You have a point x here on the boundary. This is omega or m. The boundary, you have a direction. You consider the geodesic starting at that point with that direction. There is a unique geodesic. There may be other geodesics joining these 2 points, but there is given a direction, there is a unique geodesic with that direction. Okay, and so what we do is you have a function here. We integrate the function along geodesics. To recover A0, you need to integrate the function along geodesics. This A0 here. Yes? Yes. No, you're trying to find A0. No, but that's the Q term. I didn't write that. It's true. You have the. Yes. To. Sorry? Is that the equation? I wrote the question. This is a typo here, sorry.
Is this the same phi from the icon?
No, this is the transport equation. I think I wrote it incorrectly. Yeah, it's the Laplacian of phi. So this is a typo here. Thank you for pointing it out. It's Laplacian phi times A0, so please correct. I will correct this in the slides. There is a phi missing here. There's a phi missing. It has to be a linear equation in A0. Not second, that will be second order, right? So it's 1/2 c squared Laplacian phi times A0. Okay? Laplacian phi. Phi has already been found, right? That's the solution of the Conal equation. So the transport equation is the first order. I wrote it incorrectly here. I was missing the type. I was missing the phi. Can I write over this? No, it doesn't work. So let me write it here. Transport equation. So this is a typo there. Laplacian E dot gradient of x A0 plus 1/2 c squared. Oh, not enough space. Let me write it smaller. So I'm missing the phi. Yeah. Okay. This is an ODE. By using this vector field, it's reduced as an ODE that can be solved. And then you integrate along geodesics. The vector field, remember, this is dx ds. Here, what I was saying before is the gradient of x phi, right? And x are the geodesics. So you're integrating along geodesics of this metric. Okay. We define geodesics in phase space. This is the projection. Geodesics are the projection in x space of the bicharacteristic, null bicharacteristic curves. Right? Okay, so this leads to the integration of functions along geodesics. Tau of xc is the exit time of the geodesic. So for this, we're assuming it's non-trapping. That means there is an exit time. This is finite. So tau of xc is the exit time. And it's assumed to be finite for all xc. So there are it's called non-trapped geodesics. So this is the geodesic starting from the point x in direction c. Okay, another exercise here is this corresponds to the linearization. This problem is nonlinear to recover the sound speed c from the distance function, because look at this. This is nonlinear. Sigma is nonlinear. This part is nonlinear in c, right? It's 1 over c. And you're trying to recover c for the infimum. You take the infimum of all of this. It's highly nonlinear. So you can, as usually when you have a nonlinear problem, you can linearize it. And you can check that this is it's called the geodesic X-ray transform. In the case c is equal to 1, this is the integration along lines. It's the X-ray transform that we had before. Right? These are geodesics, for instance, in the case of the sphere. This is called the Funk transform. You integrate along big circles. Right? The geodesics are the big circles where the planes try to go along big circles from one point to the other. Right? So this is called, by the way, the Funk transform, integration along circles. So this is a very important transform. It's linear because it's integration of a function, so it's linear. So there is for the X-ray transform, we saw before that there is a explicit formula to invert it. For the geodesic transform, we don't have such an explicit formula. We want to find one, but this. So, however, you can prove that it's injective. That means it's IF is 0. And in the simple case, remember the simple case is there are no caustics, no conjugate points. The behavior of the geodesic is very nice, and the boundary is strictly convex. So if this is 0, then F is 0. And moreover, there is the stability estimates, meaning that if two sound speeds are close, and you have that, if IC of F is near 0, let me put it that way, then F is near 0 in appropriate norms. However, reconstruction is not known, except in particular cases of the C. For instance, when the curvature is constant negative, for instance, known explicit formulas, but not for the case of a sphere, big circles. This is also there are explicit formulas, but it has to be constant curvature or things like that to have explicit formula. Okay? So that will be another interesting exercise for you to find explicit formulas to invert this transform. Yeah. But however, remember for the people who know about pseudo-differential operators, so this is the geodesic transform. If you assume that the projection of the projection from here, the V, the C variable, into the geodesic going through the point X, this is at the point X. In the direction B, this is a diffeomorphism, this is a strong condition. This is an elliptic pseudo-differential operator. Remember the case C equal to 1. I star I is minus square root of minus the Laplacian, minus square root of the Laplacian. So the inversion formula is, in that case, is very nice and simple. I star I of F I'm missing a constant here, times F. It can be inverted by the square root of the Laplacian. It's a non-local operator, but this is very general. In fact, it's an elliptic pseudo-differential operator of order minus 1. Look, this is of order minus 1. Laplacian is of order 2, minus the half. And the principal symbol, pseudo-differential operators have the highest order term is C of x times C minus 1. Like the principal symbol of this is C to the minus 1. Remember, by Fourier transform, to compute the symbol, you just need to take the Fourier transform, and that gives you modulus C to the minus 1. This is for the people who know pseudo-differential operators. I don't. So there is an inversion of this modulo smoothing operator, so you can recover singularities, but not explicit inversion. Okay, I give a proof of this, that this is, let me give you the formula. you can compute this explicitly. Next exercise. This is the exponential map in the direction b. Again, this, you need to know a little bit of geometry to do this. And there is you can find this formula for I star I. The question is how to invert it. So this is the distance function to the n minus 1. So remember another expression for I star I in terms of singular integrals applied to f at the point x is equal to f of y divided by x minus y to the n minus 1 dy, right? This is an equivalent expression. This is called a singular integral. Singular integrals are the same as pseudo-differential operators. The singularity is at x equal to y. We saw this earlier. And in this case, is the distance function to the n minus 1. So this is the distance in the case the metric is Euclidean. The standard metric, this is the distance between x and y. So this is the same formula, but here there is a Jacobian term, which is 1/2 the distance xy squared, the determinant. Just take the second derivative of this, you will find that in the case of the Euclidean metric, this is just 1, or a constant. Okay. So this is, okay. So to finish this, the Gelfand problem, and then I'm going to go to nonlinear equations. We want to deal with the problem of caustics. This problem when you have, you start at a point and then geodesics come together, right? Like in the North Pole for the standard metric and so on. So we want to take into, because remember we needed a condition, the simplicity condition is not is a nice condition, but it's not satisfied in most cases. In the Earth, it's not satisfied. Morse median, you know, the geodesics come together, they're called, again, caustics and so on. And you define, you need to look at the behavior of all the geodesics, not the ones who just minimize lengths. Some geodesics, when you have a point on low velocity, some geodesics are hard working and will go through the point x0. But they will take longer time to get outside. It's not the first arrival time. You need to go to look at the consequent arrival times. How do we model that? So the way I model that is the following. You take a point, a direction of a geodesic, I follow it, and then assume there is non-trapping, and I take the point of exit and the direction of exit. So I map the point. This is again a phase space, looking at phase space. A point and direction, there is a unique geodesic, follow it, and I map it to the exit point of the geodesic and the direction of the geodesic. Okay? So this is called the scattering relation. So if we know the direction and point of entrance of the geodesic, then we know the direction and point of exit. Because when geodesics come together, they start in different directions. This is C1 and this is C2, right? So the direction distinguishes the geodesics. So that's the way we're going to deal with caustics. Okay, and then there is an additional, I'm going to give myself, which is not clear that you need it, also the distance function, so the first arrival time. It might be enough. This is one of the open problems that I will give on Friday. It might be enough to just look at the scattering relation to recover the sound speed. So the conjecture is, let me tell you the conjecture, I will point this out as an open problem. We know some, I will tell you what we know. that the scattering relation now recovers the sound speed. You solve this problem, you solve the other problem. I will the problem of the boundary rigidity to recover the sound speed from the distance function. So looking at phase space is always convenient. We are going to add an additional information that you know also the distance function. So I'm adding the scattering relation plus the function, what we had before. And the inverse problem is, do all these two things determine the sound speed? Of course, again, it's an idealized problem. We want to solve it constructively so we can discretize it.
Alpha C and DC carry the different information. Alpha C may determine DC.
Yeah, alpha C is different information than DC when you have caustics. Yeah, when we have no caustics, it's the same. So this is exactly what I want to point now. So the problem is if these two information recover the sound speed. In the case of simple, this is equivalent to this. The reason is the following. I have to get better at drawing the line. So remember, what does it mean to be simple? Simple means that there are no caustics. So the geodesics don't come together, and the boundary is strictly convex. Okay, so a very nice behavior of the geodesics like we had before. The geodesics behave very nicely, like this. But if it is simple, if and only if, another exercise, the distance function is smooth, when x is not equal to y. It's continuous in general when you include x equal to y, but it's smooth. For instance, when you have non-convexity, you have this situation that you have this type of thing. So you have to go outside. So the distance function will change a lot when you go to this point, right? Because the geodesic has to go around to be inside the domain. So the distance function is smooth. So the direction is obtained. C, the direction of entrance of the geodesic is by just differentiating with respect to x. The distance function. When you have the 2 points, and eta is the gradient with respect to y. This is if x is different from y. So you have 2 points, x and y here. To obtain the direction of entrance, you differentiate the distance function with respect to x and the exit with respect to y. Okay? And so, therefore, it gives you the same information. If there are caustics, the distance function is not smooth or not convex. Okay, so let me tell you how we're going to go around caustics. I have 10 minutes, I'll finish with this. The idea will be to solve the problem locally. What I mean is the following. It's like peeling an onion. You solve, this is the boundary. You solve the problem close to the boundary, and then you march in. And here, that means you take into account only geodesics joined in this type of situation, these points. You don't take this geodesic. This is not allowed because it's not in the region. It's partial data. You don't need all the geodesics. That's the point I want to make. And in this way, you avoid caustics. I mean, there are caustics, but the caustic will be if you include all the geodesics. Oh, what happened here? Can somebody help me with? Sorry. Oh, okay, great, thank you. So, if this is strictly convex, the boundary is strictly convex, there is a unique geodesic locally, if this is sufficiently small. There is a unique geodesic. There are no caustics near the boundary. The caustics only arise when you go to take this type of geodesics. But near the boundary, and we're not taking into account all the geodesics. We take into account only the geodesics near the boundary that have no caustics. Okay? So this is a result that if you are sufficiently close to a strictly convex point, there is a unique geodesic in the neighborhood of the point. And then we're going to solve the problem here, and then we're going to march in. But we have to assume that we have a strict convexity here. So the manifold will be, the domain will be foliated by strictly convex. That's the condition that we'll need. But you can have all the caustics that you want. This allows for all caustics. For instance, the examples that I showed you earlier are included in this. So so we solved the problem. That means you take a point P, which is convex, you take a neighborhood of that point, it can be this, very close, it's a polar neighborhood of the boundary. And we're only going to take into account geodesics joining points in that neighborhood, not all of them. And for this, we only need the distance function because the scattering, you don't need the scattering relation because there are no caustics. Right? You don't need it. And the question is, does the distance function between points here in the neighborhood of the point P determine the sound speed locally? Once they determine locally, then you march in. It's like peeling an onion, right? So in dimension 3 or higher, this is what we prove. Is the boundary strictly convex near points for two speeds. The distance function is the same. You remember, it depends on x and y near the point PP, then c equal to c tilde near P. But not only uniqueness, that's as I said before, a good uniqueness proof has to lead to stability, meaning these are close, then the sound speeds are close. There's also reconstruction, I will show you, and there has been also numerical reconstruction, not just, I will show you some pictures. Yes. This is paper with Andros, yeah.
And do you assume C is smooth?
Sorry?
C, the wave speed is smooth.
Smooth, yeah, this is smooth, right. You can generalize this. I gave this problem to one of my students, to CK. The ideal situation will be C11 for you're interested in this because geodesics are well defined in that case. Because it's a Lipschitz, geodesics you solve an ODE, you have to have Lipschitz coefficients, and that happens when you have if sound speed is lower than that, then you may have branching of the geodesics. You can. And there's that's also an interesting problem, when you have broken geodesics or branching, or you have several geodesics. Anyway, this
Dimension is 3.
3 or higher. In dimension 2, this is not known. This is one of the problems I'm going to propose on Friday.
It's also related with CPS?
No, no. It's the inversion of the geodesic transform. And in order to continue, I need this condition that the point be strictly convex, because you need the geodesics to stay inside. So in order to guarantee that, I assume that there is what's called a foliation, meaning for every point there is a strictly convex hypersurface. So I want to make sure that if I am at the point here, so so far I have progress. Oh, sorry. Let me draw the line. I have managed to get inside a little bit, but I want to continue. By the way, we know exactly how much do you need to go. Okay, so because we need to fill the domain. That's why the stability is very important, right? Okay, and then I need to have a strictly convex point to continue. So that's why I assume this cannot be guaranteed in general. Well, I would like to know whether it's true in general, but I don't know. And then you can continue until you fill the whole domain. So this is called layer stripping. You mean you go strip by strip, or peeling the onion. This is more cooking type.
Is it a part of your assumption or?
It will be assumption.
Ah, okay. I thought.
But this allows for caustics. This allows for any caustic that you want. Because in dimension 3 or higher, we have enough freedom. We don't need all the geodesics, that's the point. We're only going to use part of the geodesics. So here we use only this, and here we use this, right? Not all the geodesics. Yes?
So the injectivity of the axial transform in foliated dimension manifold is still open.
Yeah. I will mention this Friday. In 3 dimensions has been solved. The physical problem is really 3 dimensions, right? But 2 dimensions is interesting mathematically. You have more tools in 2 dimensions. However, this problem seems to be harder in 2 dimensions. So one of you need to come up with a new idea. So in dimension 3 or higher, so you have 2 sound speeds and it's strictly convex. So I assume that this can be this is the assumption. You were asking, this is an assumption. Can be foliated by strictly convex surfaces. If this happens, then the sound speeds are the same, and you also have stability and reconstruction. So you're asked, when is the foliation condition satisfied? Is it satisfied for a strictly convex domain? This is for the people who know this word. Non-negative sectional curvature. For instance, the sphere is an example where the curvatures are positive. And this is the most interesting case because when you have positive curvature, the geodesics come together. Right? And then you form caustics. But this is why we can allow a lot of caustics. The examples I showed before satisfy this condition. Also, you have non-positive sectional curvature, and you have something called no focal points. I mean, this is also, if the sound speed increases with depth. This is a condition that means that the derivative, so suppose it's radial, that was proposed by, in the first results about this were by Herglocks. he assumed that the Earth is spherically symmetric. The sound speed depends only on the radio. He assumed this condition. So that's the sound speed increases with depth as you go along. This is satisfied. And then he found an inversion formula. In this case, there is a formula. This was, by the way, before the Radon transform, 1905, the year, the famous magic year of Einstein. Inversion formula in this particular case, the sound speed depends only on the radio. This was used for the first model of the Earth. The first model of the Earth was spherically symmetric and used the Hercules inversion formula to recover. Okay, so I don't have time to talk about this, but there's some numerical. We can invert quite explicitly the geodesic transform, the local geodesic transform. But this will be in the notes and in the slides. Here with Au and Eric Chen at Hong Kong. These are at the Hong Kong. Au was a student of Chen at the Chinese University of Hong Kong. I didn't do any of the numerics. I just told them, the theory behind the inversion for the geodesic transform. So you have this function you try to recover from the integral. And this is another example. It's different function, but let me show you the most interesting case. This is the relative error. There is a Neumann series that you use to invert. These are how many steps you go in the Neumann series for the different functions. You get better and better error. But this is for the nonlinear problem. There is a benchmark in geophysics called the Marmouzy model. And this is a spherical section of the Marmouzy model that has very complicated sound speed, has many caustics, and has even trap rays. The foliation condition implies that there are no trapping. So the method that we have have been realized numerically too. So it's numerical reconstruction in that case. Don't ask me how this is done because I don't know. Okay, so I finished with the Gelfand problem. There will be more details in the slides, and even more details. I will give some notes that we are working, and I will have even more details. And eventually, there's supposed to be a book. But okay, I cannot give all the details; it's impossible. But just the main idea. Any questions?
So your theorem doesn't contain the non-trapping condition, right?
It is, yeah, but however, the foliation condition implies non-trapping.
Which implies
The foliation
foliation
condition implies non-trapping. Yeah, because the results about trapping are. There are some results by Guillermo and others about when you have trapping, but the trapping is very small. It's called hyperbolic trapping, has measure 0. It's not, in my opinion, the most important difficulty are conjugate caustics, conjugate points. That's more than trapping.
Not we'll send Gunther, and then we'll start our break. And let's all go out for a photo first and enjoy coffee.
No. This is not a.
That's the end.
Okay, I'm going to make sure that I don't. I think so. Let me make sure. Yes, yes.
So you mentioned this example of an additional example in order to proceed the recipe. So if we have like the empty, then like pretty much the links, yeah, the distance, and then we kind of choose the correct one. So the simplicity condition kind of means that we don't have such peaks, so they are just either mellowed down or okay.
You have no regions of non-velocity.
Okay.
For instance, this formation.
Okay. So in that example from like Uhlmann, he like where he had like simple case and non-simple case. So in the simple case it was getting mellowed down, and in the other cases it was getting more subjective.
Yes, regions of non-velocity. You need to go and take your picture.